We've talked in the past about casts in C-style notation, where you have a data type inside parentheses that you use to convert the data type of some expression. In Lecture 8, we're going to take a deeper look at type conversion methods in C++, and we're also going to take a look at what's called runtime type identification, which has to do with figuring out on the fly what actual derived kind of object, a pointer or a reference to a base class object, is really pointing to or really referring to. You can request an explicit type conversion in C++ using the old-fashioned C language style typecasts. There's also a slightly improved function-like type conversion that the C++ language provided early on. In more recent versions of C++, there are 4 named type conversions that you should use in preference to the C-style typecasts or C++ function-like typecasts. And in C++ 11, construction using curly braces was added to the language. So this is unfortunate that we have several generations of notation for performing explicit type conversions. It would be nice if the older styles had been thrown out of the language when the newer styles were introduced, but of course that would have ruined the backward compatibility of the language. So here on slide 3 is how you do a C language style typecast. And we've done this before. You put a data type name inside of parentheses, and you put that in front of an expression. Whatever the type of the expression is, it will be forced to be converted to the data type name in parentheses. Now, C-style casts are completely unsafe. When you use a cast, you are saying to the compiler, "Hey compiler, I'm smart, do what I say, and don't complain." And so the compiler will not do any error checking. The compiler will just do what you tell it to do. Here on slide 4 are several different ways of using C-style typecasts. Here we have an int value of 2, and we would like to do floating point double precision arithmetic to evaluate this multiplication and division. So one way of accomplishing that is to force the 2 to be treated as a double. That will cause the multiplication to be done in double precision and also the division to be done in double precision. And we end up with 3.333, etc. as our double result. As another example, here I have an int value written in hexadecimal. Perhaps my documentation for my computer tells me that there is a serial port, some kind of input-output port, from which I can read data and to which I can write data at a particular location in memory, specifically at this location hex 0FFA68BC. Well, it would be convenient for me to have some kind of IO port class that describes what all the bits and bytes are in this IO port hardware device in my computer. And so I can set up that class or that struct, and then I can create a pointer to an IO port. Here the name of the pointer is PIO, and I can force PIO to contain that integer address cast to a pointer to an IO port. Now in this case, the compiler will not actually change the value in any way. The value is still going to be the int that you wrote down as a constant, but it will allow you to just take that integer value and shove it into a pointer, so now you can interact with whatever is at that address through this PIO pointer. Another thing that C-style casts can be used for is to get rid of constness, which is almost never a good idea, but a cast will allow you to do this. Here I have p set up as a pointer to a char const, specifically initialized with the address of the little h in the string literal hello. So the string literal hello is going to be stored in the static data area. That's 6 characters, HELLO, and a null character. And p is going to be initialized with the address of the little h. Now, string literals in static data are intended to be const. Maybe your compiler will allow you to change what's in a string literal, or maybe not. If you want to try to change what's in the string literal, you can use this cast, open paren, char star, close paren, in front of the pointer to say, all right, I know I have this pointer to a character const, but I want to treat it as a pointer to a char that is not const, And then I will use the star to do a dereference or an indirection on that pointer and assign a little j into that location. Now, depending on your compiler, depending on your system, maybe that will store a little j in place of the little h. Maybe that assignment will simply be ignored. Maybe that assignment will cause your program to crash. Since what we're using the cast for here is an illegal thing, namely eliminating the constness of a const, you will get what you deserve on your system. Yet another thing we can do is take a base class pointer. Here I've got PE set up as a pointer to an employee, and I can force that pointer to be treated as a pointer to a derived class object. So here I'm taking my pointer to employee PE, and I'm forcing that to be treated as a pointer to a manager, which I'm storing in this variable PM. Now, maybe this will work. If Bill is actually a manager, then I am allowed to take the address of Bill and store that pointer to manager into a pointer to employee variable. And I would also be able to take that pointer to employee and convert that into a pointer to manager, and everything would be fine. But if Bill is not really a manager, and now I try to do something with PM, like PM arrow get budget to get the budget of this manager, if Bill is not really a manager, I'm just going to get some kind of garbage, whatever stuff is sitting around in memory after the employee data members that Bill actually contains. Okay, so C-style casts are very powerful, totally unsafe. If you use them and you know what you're doing, you'll be fine. If you don't know what you're doing, mysterious things are going to happen, your program is going to crash, you will deserve what you get. Now, when Strustrup developed the first version of C++, he felt that the notation for C-style casts was ugly, and so what he permitted was function-like casts to accomplish the same purpose. For example, if I want to treat 2 as a double, then in the function style of type conversion, I would use the name double as though it were a function with integer 2 as my argument, and that will force the integer 2 to be treated as a double precision 2.0, and so forth. Now, frankly, the function-like type conversions are no safer than the C-style typecasts, and furthermore, they're a little bit harder to use, because let's suppose that I wanted to treat this integer value, hex 0f fa68bc, as a pointer to an I.O. port. Well, pointer to I.O. port is not a name, so I first have to create a name, which I'll call I.O. port pointer, using typedef. So now I can use that name in the next statement as though it were a function to convert that integer value into an I.O. port pointer, which is simply an alternate name for pointer to I.O. port. That works fine. It allows me to use the function style type conversion from the early days of C++, but notice that I haven't gained any safety, and I've had to write 2 lines of code now in using a typedef rather than the 1 line of code that I wrote over here on slide 4 using the C-style typecast. The named type conversions that we're going to take a look at here starting on slide 6 with constcast were introduced as a somewhat safer and somewhat more clear method for standardizing the 4 different uses of casts that we've illustrated back on slide 4 with our C-style casts. Now, it's important to understand that these are not really safe. You can still do stupid things using these casts, but you will get a little better support from the compiler. And of course, it's much easier in your editor or in your integrated development environment to do a search for const_cast as opposed to trying to do a search for a pair of parentheses, because of course parentheses are all over the place in C++ code. Okay, so I have cleaned up all of my highlighting on slide 4 so that we can see how the 4 named type conversions relate to the 4 examples of using C-style typecasts that we looked at on slide 4. Const cast, shown here on slide 6, is only able to alter the constness of an expression. That is, it can add constness to an expression that is not const, or much more commonly, it can take away constness from an expression that is const. So using const cast here on P accomplishes the same thing that we did over here on slide 4 using an ordinary C-style cast. That is, P is a pointer to a char const, and what we're using const cast to say is take P and treat that as a pointer to char. So we've eliminated the constness from P, or technically from the thing that P points to. The way you use const cast is to give the data type that you want to convert to in a pair of angle brackets, and then the expression that you're trying to convert is put in parentheses following the angle brackets. So const cast, open angle bracket, char star, close angle bracket, and then paren P is how you indicate that you want to take P and convert that to a pointer to char. Now, adding or eliminating constness is the only thing that const cast is allowed to do. It's more restricted than a C-style cast, which can do anything. For example, if you attempted to use const cast, as we're doing here on the bottom of slide 6, to convert P into a pointer to int, this would give you a compile time error, because not only are you eliminating const there, but you're actually attempting to change the data type of P's value as well, and that's not allowed. So the named casts are more tightly focused and hopefully makes more clear to the developer and makes it safer in the compiler to narrow the kinds of casts that you're doing. Next, we're going to take a look at static cast. Static cast can be used to convert pointers to and from void pointers, and also can be used to do numerical conversions, such as double to int or int to double and so forth. Here I'm taking I, which is an int, and I'm converting the address of I, whose data type would be pointer int, into a pointer to void using my static cast. So static cast here is taking an int pointer and converting it into a void pointer, which I can then successfully store in this void pointer variable PV. In the next static cast, I'm taking PV and I'm converting that into a pointer to unsigned char using static cast. So this is the same address. It is originally the address of an int. I've converted that to a pointer to void, and then I've converted that into a pointer to an unsigned char. Why would we ever do such a thing? Well, an int is, on our systems, 4 bytes long, and there are 2 different styles of organization of bytes in an int on different processors. One style is what's called little endian, which stores the low order byte in the first address up to successively higher order bytes. And the other style is what's called big endian, which stores the big order byte first down to the low order byte last. And so what we might be interested in doing here is determining whether the 127 that I contains is stored in the first byte at that address or stored in a later byte in that address. Okay, so if 127 is stored in the first byte at that address, that implies that we're working on a little endian processor as opposed to a big endian processor. Now, you can use static cast to convert to and from pointers to void, but you can't use static cast to convert directly from one specific pointer type to another specific pointer type other than void. Here, if I try to take the address of an int and convert that to a char pointer, the compiler will complain at me. So static cast does allow me to convert from one kind of pointer to another, but it requires me to be careful and thoughtful about how I do this. Static cast can also be used to convert among numerical types. So static cast could be used in the way that we're doing over here with double on slide 4, it would allow us to take an int value and convert it to a double, or a double value and convert it to an int, and so forth. Reinterpret cast, shown here on slide 8, is the one that allows us to handle all bets are off conversions from non-pointers to pointers and vice versa. It's the one that will allow us to take an integer value representing the address of something in memory and convert that into a pointer. So here we're doing essentially the same thing as we did over in our second example on slide 4, but using the more carefully checked named cast as opposed to the C-style cast. Dynamic cast handles conversions of base class pointers to derived class pointers. That is, dynamic cast allows us to do the kind of thing we did here on the bottom of slide 4, take a base class pointer and convert that into a derived class pointer. But dynamic cast will only do that if the base class pointer really is pointing at a derived class object. So of the 4 named type conversions, const cast, static cast, reinterpret cast, and dynamic cast is really a new feature that we didn't have using the old-fashioned C-style casts. And we'll have a lot more to say about that later. It's also possible, as shown here on slide 9, to use curly braces to do type conversions. This is sort of a function-like type conversion. That is, we give a type name like double and then some expression in curly braces. This typecast will only be permitted if the conversion is what's called a non-narrowing conversion. That is, it's fine to convert from an int to a double because all int values are guaranteed to fit in a double object. But if you attempt to go in a narrowing direction, that is, if you attempt to convert from the double 3.4 to an int, well, an int would chop off the fraction part. This is what's called a narrowing conversion. And so you'll actually get an error from the compiler if you attempt to do a conversion in this way. So in other words, the curly braces can be used to perform guaranteed value preserving conversions. That is, from little types up to bigger types, not from bigger types down to little types. In this final example, you might argue, well, 5 stored in an int can fit into a char perfectly fine, but the curly brace type conversion does not consider the current value of j. It just considers the type of j, and since j is an int, and there are many values of int that won't fit into a char, if I attempt to convert j's value into a char, the compiler will give me an error. So the various forms of casts and curly brace construction are explicit type conversions that the programmer specifies that they want to do. There are also, of course, implicit type conversions that the compiler does for you, and of course we've seen this in things like this arithmetic expression in which we have a double, 2 ints, a bool, and a char. This thing is going to be evaluated from left to right within precedence levels. So the division actually has the highest precedence, and so very likely this is an error on our part. 7 divided by 3 is going to be exactly 2, the int 2. And only then, after that division is finished, will the 2 that results be converted to a double so that we end up with 12.5 plus 2 is 14.5. Then we subtract 1.0, which is what happens when we convert true to a double. And then we add 49.0, which is the ASCII value of the character 1 converted to a double. All right, so this expression here compiles and runs just fine. We may be surprised by the result if we weren't aware that we were going to get an integer division here before the addition and subtractions occur. But the compiler simply does this for us and doesn't display any complaints or warnings. Now it turns out, and this is sometimes a nasty surprise, that if you have a constructor for a class that takes a single argument, that constructor will be used to do an implicit type conversion from the argument to an object of that particular class. And this often happens by accident and leads to problems. For example, here on slide 11, we have a function named compare, CMP, and what CMP takes is two arguments, each of which is a reference to a manager const. In the implementation of the CMP function, we're saying, all right, if M1's rate, that is, if M1.getRate, is greater than M2's rate, M2.getRate, then we'll display a message saying M1.getName has a higher rate than M2.getName. This seems quite reasonable. You receive two references to manager const, you compare their rates, and you print out a message if the one on the left has a higher rate than the one on the right. But you may remember that we introduced default parameters into our manager class back in a previous lecture. So the manager constructor that we have now takes a name and a rate and a title and a budget as arguments, but only the name is required. We had default values, 70 for the rate, manager for the title, $500,000 for the budget, and consequently, even though we think of the manager class constructor as having 4 arguments, it can actually be used as a single argument constructor, and here's where that happens. Al is a manager object that we have initialized using all 4 argument values. Name is Al, rate is 55.5, title is boss, budget is $250,000. And above Al we have Bob, which is simply a string initialized from the string literal Bob with a capital B. Now you would think that if I pass Bob as an argument to CMP along with Al, that would fail because Bob, after all, is just a string object. The problem is that our constructor is willing to build a manager object from a string object by applying the default rate, title, and budget. Consequently, we end up with a manager object automatically constructed with Bob as the name, 70 as the rate, manager as the title, and $500,000 as the budget. All right, so the default rate for Bob, for this magically created manager object called Bob, is $70, and so we get a message out on our screen that Bob has a higher rate than Al, because 70 is greater than 58.5. So we may have intended this to work this way, but more than likely it's an error. We can prevent this error from occurring by putting the word explicit in front of the declaration of each constructor that can be called with a single argument. Here we've done this on slide 12, both for the employee constructor, which receives a required name argument but an optional rate argument, as well as for the manager constructor, which takes a required name and optional rate, title, and budget arguments. Once you've declared the constructor explicit, that means it won't be implicitly called like it was here for Bob on slide 11, and instead, if we want to convert Bob to a manager, we have to explicitly call the manager constructor for Bob. So if I just tried to do a CMP of Bob and Al like I did back on the slide 11 program, the compiler would yell at me that I'm doing an illegal implicit conversion. But if I do an explicit conversion by calling the manager constructor directly, this is going to be allowed. And it also, frankly, makes more intuitive sense. Next up, we're going to take a look at runtime identification, so-called RTTI, which makes use of the dynamic cast name type conversion that we introduced a little bit ago. Now, the cool thing about dynamic cast is when you give it a base class pointer as a value to convert, then dynamic cast tests whether this pointer actually points to the specific type of object identified by T. All right? So that's all very theoretical. Let's take a look at a specific example. Over here on slide 15, I have a function named giveRaise, and I'm passing into this function a pointer to an employee. Now, actually, that pointer to employee might be pointing at an employee, or it might be pointing at a manager, or it might be pointing at a CEO. And so this is where dynamic cast comes in. If I say convert PE to be a pointer to a CEO instead of a pointer to an employee using dynamic cast, what will happen is if the kind of object that PE is pointing to is a CEO, then I will get back a pointer to a CEO. But if the kind of object the PE is pointing to is not a CEO, then I will get back a 0. And 0 in an if test means false. Okay, so let's suppose that our pointer to employee really is pointing at a CEO. Then the dynamic cast of the employee pointer to a CEO pointer will succeed. I'll get back a non-zero pointer to a CEO object here, and I can then call the setRate function on this pointed to CEO, and what I'm going to do to set the raise for the CEO is to get the current rate that the CEO has and increase that by 10%. So the CEO gets a 10% raise. Okay, so to skip back to slide 14 for just a moment, if a base class pointer really is pointing at a derived type object specified as your dynamic cast type, then you will get back a pointer to T. Otherwise, you'll get back a null pointer, or 0, which will test as false. This process of examining a base class pointer to test whether that base class pointer is pointing at a derived type of object is referred to as downcasting, and this is somewhat frowned on in C++ for various reasons. In other languages like Java, it's the conventional way of doing business, so I'm not going to really express a deeply held opinion about this. Alright, let's suppose that over on slide 15 we get a pointer to an employee passed into giveRaise. We attempt to do a dynamic cast of that pointer to CEO, but this time what that pointer is pointing to is not a CEO. So that's going to fail and give us null pointer, and we drop down to the next if. See, here we have an if that fails, so we're going to say else if, and here we're going to test whether that employee pointer is really pointing at a manager. If that employee pointer is pointing at a manager, then we're going to give the manager a 5% raise over what the manager currently has. Finally, our class hierarchy is only 3 levels deep, so if the pointer was not pointing at a CEO and also was not pointing at a manager, we must be pointing at a regular employee, and so we'll give a 0.5% raise. Obviously, it's better to be a CEO, but this illustrates the idea of what's going on with the dynamic cast. Here on slide 16, we have a program that's making use of a manager object, an employee object, and a CEO object, calling giveRaise on each one by passing the address of each of these objects, and then displaying the new rate after the raises have been applied. So Doug is a manager. When we give a raise to Doug, Doug is going to get a 5% increase, so that's going to be a $3.25 raise. Ed is an employee, so Ed is going to get a 25-cent raise, and Frank, the CEO, is going to get himself an $11 raise. And so the output of our program looks like so. Clearly you don't want to be an ordinary employee at this company. Let's take another look at this getRaise function back on slide 15. I wanted to point out that the order in which we did these dynamic casts was not arbitrary. If you have a hierarchy of classes and you want to try to identify which specific kind of class in that hierarchy a pointer is pointing to, you need to arrange your sequence of if tests from the most derived level down to the base class level. So here, since we have employee as our base class, and a manager is a kind of employee, and a CEO is a kind of manager, which is a kind of employee, we did our check for the CEO first, Then if it wasn't a CEO, we did a check for a manager. And if the pointer was not pointing to a manager, then we knew that it had to be pointing to an employee. Now, if we switch these around in the other order, and we tested for employee first, well, PE is a pointer to an employee. And so any PE that comes in is going to be an employee. And if we tested for an employee first, that test would always succeed. And we would not get down to doing the manager test or the CEO test. Okay? Because if PE is pointing at a CEO, since a CEO is a kind of employee, PE is also pointing at an employee. And so if we did a check whether PE was pointing at an employee, we would discover, oh, that's true. Okay, so the order in which we did this, from most derived down to base, is very important.